14 parties in conference, including you. Mute on.
And, all right. Oh, yeah. I don't know why that does it. Unfortunately, we're still going to hear all the beeps. Sorry. That out of the way. All right. Okay. Should we start? All right. Well, thank you for being here at this seminar, and thanks for Partha where he recommended that we share this with WSS. So Partha Lahiri, Dr. Partha Lahiri, is a professor in the Joint Program in Survey Methodology in Maryland. His research interests include sampling, official statistics, and small area estimation. And I'm really excited to hear about data integration. It seems a new area maybe, but still, I don't know, connected with the old. I guess we'll see. Finally, Dr. Lahiri is a fellow of the American Statistical Association and the Institute of Mathematical Statistics, and he's also an elected member of the International Statistical Institute. So welcome, Dr. Lahiri. I'll get out of your way. All right, thank you.
First of all, I would like to thank you for inviting me here. Thank you, Wendy and Mikhail. I gave this talk, I think last month in Singapore at a ISS satellite meeting, and I thought maybe I can repeat that here. I can see Mikhail there, he was there, so he was the only guy. We'll be hearing a couple of times, but make some revision, so hopefully it might interest you.
Yeah, I'm going to interrupt for a second. Do you mind that you're closer to the mic?
Okay.
You're closer to here? Okay, I'm sorry. That's perfect.
Is that okay?
Yeah, that's perfect. Yeah, thank you.
Okay, so couple of years back, there was some planning for a conference in Singapore, and I kind of suggested what about statistical data integration workshop, and that's where it started. And then they asked me to give the talk on statistical data integration, so I had to think about what we really mean. And then I gave some thought, and it seems to me that it may mean different things to different people. But I guess in order to talk about this topic, at the minimum, we should have 2 or more data sets that will make data integration relevant. But then what do we do with data integration? Then we may have some specific purpose, and we may want to talk about data integration in that specific context, or we may not have any immediate purpose. Maybe we are trying to integrate data for multi-purpose. A lot of times, and with that, I will just say that data integration is something, at least to me, means that you try to combine or extract information from 2 or more databases for doing certain things, or for just creating it for multi-purpose use. That's how I'll define it. And the way I organize this talk is I'll start with some very old example, and then I'll give you some possible examples of data integration that some of you may be interested in. And then I'll be talking about some specific integration problem that I got involved with either with my student or my collaborator. So that's the organization of the talk. So I said that data integration you may want to do for some specific purpose. So the first purpose I'll talk about is, can we integrate data, or can we extract information from multiple databases to reduce certain kind of non-sampling error? And the reason I picked this example because there was a famous example and it's an old example. And so with that, I'll go to the next slide. I hope this will work. Yeah, that's what I'm using.
No, I mean on the keyboard.
Oh, keyboard, I see.
Yeah, it might not work. I don't know if it works with PowerPoint. I mean, Adobe.
Yeah.
Is there like a... Oh, maybe.
Page up, page down.
Page up, page down?
Yep.
So page up is the one, no, page down maybe. Page up?
Like, you better fix it. Maybe if you have it on,
Now it's
working. So, I picked that example from the famous book by Hansen et al. In 1953, basically page 483 to 486. This problem is described. The problem they talked about is estimation of median number of radio station heard during the day for over 500 counties in the U.S. I put in brackets small area because I have some comments later on. But for the moment, let's see how they introduce the problem. So they have a mail survey, which is not a small scale survey. They have about 1,000 families per county. So if you consider 500 counties, it's 500,000 families they're talking about. So, but there are a couple of problems. One is the incomplete list frame, and which can cause coverage error, and the other one is response rate was very low, and it was reported as about 20%. Okay, so of course you can make estimates out of this estimate of median number of radio station heard out of this survey, but although a sample size is not that small, it's even when you consider there is number of respondents, there are like 200 people per county, not that small, but it has problem in with respect to the incomplete list frame, the frame error, and also the non-response error. And specifically, for example, if the people that you leave out in the frame is very different from the people in the frame, that could cause a severe bias. And likewise, for if the non-respondents are very different from the respondent, it could create another bias. But of course, you can make this estimate, and let's call it Xi. So Xi suffers from these two kinds of non-sampling error. So what did they do? So they, is that page down? Page down, okay. Oh, it works. So they talked about another survey. Take help from another survey, which is well designed, and the assumption is this survey is much better than the previous survey. It's a personal interview survey, okay? But since it's a well-designed and expensive survey, they cannot take a large number of observations, so they had to make some compromise, okay? So what they did basically, they grouped these 500 counties into 85 groups such that the counties within each group are more or less homogeneous. And then they decided to take data sample from only one county. Hopefully that represents that group. And remember, in the main survey, they had a problem with the frame error, and so they didn't go for that. They did area sample. And I had some discussion with Graham yesterday on area sample. So that purpose to, at least reduce the extent of the frame error. That's the purpose, the coverage error. And then they went for personal interview survey with the hope that that will do something good to the response error problem, okay? And so they went ahead and collected the sample, and then you can have an estimate, okay, for each of one of these 85 counties just direct survey weighted estimates. You can call that YI. So in the book, so the simple thing you can do a plot, scatter plot, where the x-axis is the median number of states, median number of stations from the mail survey, which you call X, and the y-axis is median number of stations from interview survey, which you call Y. So there will be like, I didn't count the number, but it should be like 85, and they had this fitted line, which seems to be good with the coefficient of correlation reported in that graph is 0.7, and they also have a measure which is sigma y prime minus y, and I suppose this would be the difference between the points and the line, and then they just take the standard error, but I really don't recall what exactly they did, but that seems to be reasonable. But what you can see that there is a clear relationship, in this case, straight line relationship between Y and X, between the estimates from these two surveys. And they essentially leverage this relationship, okay, to, you can say, reduce the extent of the non-response bias. So specifically, you can guess what they may have done is they had this fitted line. YI hat is the fitted line, which has 0.52 as a intercept and 0.74 as the slope. And so if you have X from the mail survey, by using this equation, you can fix some of the bias due to the non-sampling error, if you can view this way, And what they actually recommended that for the counties, the 85 counties where they have some data from the more well-designed survey, they just recommended that because they have sample size issues with that. And then for the rest of the counties, they corrected the mail survey estimate using this equation. Very simple-minded method, which makes a lot of sense. So the model was used back then to fix the non-sampling error. But we can also view this example, very nice example of small area estimation. If you believe the second survey is the prime source of information, and then you have basically data from 85 counties. They are pretty good, and you can use direct method there. And for the rest of the counties, you don't have any data, zero sample size. And we talk about this kind of small area problem all the time. So you can, of course, think that way. So this example I like because of that reason that you can explain how you can possibly reduce the extent of non-sampling error, and also give this as an example, early example, how small area estimate can be developed. This is precisely what you may call synthetic method, synthetic regression method in small area estimation. But there are questions. Of course, this was done back in the 50s, and now we have many, many different methods. So we can ask some questions. The first question we can ask, is there a way to improve this synthetic estimate, I call it, YI hat, for counties with no data from the personal interview survey? Is there any other way to improve it? They went for the synthetic method. And then how do you measure the uncertainty of this synthetic method? And then do you still use the YI, that is the direct estimate that you have from the data from the second survey, even if you have small samples? This has some implication because perhaps instead of using, instead of designing it for 85 counties, maybe you may decide to give more data to other counties. So since the budget is tight or limited, then that may rise to a situation where you may not apply direct method for any of these counties. Okay, so these are some of the questions that you may raise. Okay, so I have been thinking about it through a course that I offered at JPSM. I had a very good student, Shomujit Das. So we did some preliminary work. First of all, if you see this, for that example, incorporation of sampling variability is not that critical because for each of the county where they have samples from the second survey, they're pretty large. Okay, so if you look at the standard error, they will be very small. So for them, it was not a big issue, at least for those counties. But if you have a small sample size, maybe you want to incorporate that sampling error as a part of the model. They use just regression model, right? So you can say, okay, I have YI, that is the estimate coming from the personal interview survey, and I have 85 of them because I have 85 counties. And XI is the data coming from the first survey, the male survey, and I have data for everybody, all the 500, right? And then sigma I y square and sigma I x square are sampling variances of those estimates. For the sake of simplicity, let's say they are known, but in reality, you do have to think about estimation of them, and there is a huge literature on that. So I'm not going into the details of that. And then you might say, okay, I'm interested really in the mean of y, not the mean of x, mean of y. So I'm interested in theta iy. How can I borrow strength from other sources? So one source is, of course, the first survey data, okay? And we have seen they are highly correlated. So that could be one source that we can think of. And then the other source could be at the county level. There may be data from different administrative records, some aggregate data available, or maybe from the census record, which I call ZI. And for simplicity, I'm just considering one of them. But in theory, you can use many, actually. And that has got a variability tau square. So this is one such model you can think of. In fact, in the paper that we are writing, we have some other models. So if you think about this model, what it is doing, basically it's incorporating the sampling variability. Okay, so that will give you a better measure of uncertainty that I talked about in the previous slide, because it incorporates the variability due to these estimates, yi and xi. So that's one thing it will do. Okay. So you'll get your, if you do say mean square error type, the classical way, your mean square error will be inflated compared to the mean square error if you had just used the regression model. If you do a Bayesian analysis, you can do any Bayesian or classical on this model. That's not a big problem. But this is the scientific part of the model. Then other thing it will do, for the estimate, it will give the weighting in a more appropriate way. Perhaps if the x's are not that good, it will maybe downweight that thing. So you may be able to see this in terms of a formula. Here, what will happen that when the sample size, if the sample size is small for some of these 85 counties, it will not suggest the direct estimate that was suggested by Hansen et al. Example, which was okay then because sample size was large. But in this case, it will be some sort of weighted average of the direct estimate and synthetic estimate, depending on what kind of model you use. You may not be able to see that kind of clear-cut formula if the model that you'd like to use is a nonlinear model, for example. But this is what's going to happen. You get some information from the personal interview survey, some information from the mail survey, some from the administrative record, for example. So you can combine or integrate data from different sources. Now, what would happen to the counties where you don't have data from the second survey. That is interesting. Of course, it would be still synthetic in the sense it will purely use X, but you can think of other kinds of models. Remember that the way they have done it, they put similar counties within a group. So you can possibly borrow strength using some model. Maybe you can borrow strength through some correlation. So that's what you are going to happen. That's going to happen. So you can improve both, the direct estimate for these 85 counties, and you can have probably better estimate for the other situation. But of course, this depends on the modeling. It depends on more sophisticated modeling. So the importance of model building cannot be overemphasized. That one must do, and must do all sorts of checks. And that is true for any kind of model-based system. But this example kind of shows you that there is a use for model to integrate data, at least for reducing the extent of non-sampling error, and also for smaller error estimation problems. Okay, so then I'll say that I didn't have the data. Of course, I don't know anybody has that data. I would love to have the data, but that is not available. I could have analyzed the data, but let's just illustrate what the modeling can do for small area estimation. Okay, so if we go back here, I of course don't have xi, and let's just say I have yi and some zi. Yi is the direct estimate of a county, and zi is the administrative record, from some sources for the county level. Okay, and so you can go for the classical mixed model approach where you go for empirical based linear unbiased predictor, or you can go Bayesian approach, putting further bias on the hyperparameter, and you can go either way. But whatever way you do is going to borrow strength from both the sources. Okay, and this is a very good example from the Census Bureau's SAPI program, Small Area Income and Poverty Estimates program, and it's a county level. They're talking about school-age children under poverty. Okay, and this graph was provided to me by my former collaborator at the Census Bureau, Sam Hawla. He's not there anymore. He becomes a data scientist now in a company, and he gave me the graph, and I use it for my lectures. So what you say here is a poverty rate for Los Angeles County, one of the biggest, probably the biggest county in the U.S. I don't know, but that's what I was told. And it's a time series graph. So we have estimate for the year starting from 2005 to 2010. And what you see here, two kinds of estimate: direct estimate, the survey-weighted estimate, which is the green, and then the red one is the official estimate. Official estimate is based on basically empirical lab procedure, and I understand they are now using Bayesian method. So if you look at the two estimates, you will see there is virtually no difference. And if the method is good, that's what you would expect, because for Los Angeles County, there are lots of data. And so you would expect your model-based estimate, whatever model-based estimate you use, to have the desirable design consistency property. That means if the within sample size is very large, you should approach to the right quantity, in this case, the survey-weighted estimate. And that's nice. But what happened to a small county? So I picked up Keapaha County in Nebraska. I used to live in Nebraska for like 15 years, so I was interested in that. So Sam said maybe Keapaha County is a very small county. And again, the same graph, poverty rate over different years. And now you see something interesting. Again, the green one is direct, and the red one is official. You notice that in 2007, there is no estimate for the direct. Why? Because there is no data to estimate. Although I think in ACS design is supposed to have sample from every county, but here they are doing 5 to 17 years old kids, and for that they didn't have data. So you don't have a direct estimate, okay? And they are quite erratic. Sometimes they are very different from the official. Sometimes on top of it, like in 2008, they are the same. In 2010, you see there is a direct estimate, but no official estimate. And you might wonder what's happening. Nothing fishy here, actually. At that time, they didn't compute that estimate. I'm sure that you can find it now. And then you can do the same thing for the standard error. And if you look at the standard error of the direct estimate, they are generally higher. And again, 2007, you don't have an estimate, so you don't have a standard error. And generally, the official estimates are standard error below this thing. Here is one interesting question that I would like to raise. Maybe some of you have good answer. We have to be careful about how we compare this standard error. For the official estimates, standard error computation based on the model they used, okay, is based on that. And the standard error for the direct, I suppose this is based on some GPF method. So they are not strictly comparable, but that's what people report, and we are just comparing it. Okay. Now, so at the beginning I said, we may want to integrate data for a variety of purposes, and I had to give this plenary talk in Singapore, and I knew that people from different area will come, so I was thinking about examples. And so one is like linking of two probability samples, one nested within the other, and it's a whole problem. We can look at standard text by Cochrane. There we do double or two-phase sampling, where you may get the X auxiliary variable from the larger survey, or the Y, which may be expensive, you get from the smaller survey, And something like that, you can think about enhanced example. I was told it's drawn from the NHIS, from the bigger survey frame. And so it occurs in practice. And then we have linking of two independent survey, non-rested sample. I gave one example already from the Hansen example, but Bose in India, in Indian Statistical Institute, thought about this problem long back in 43. Apparently in those 40s and 50s, they were thinking about combining surveys. And more recently, Hitteroglu has one paper, and Jay Kim and John Rao has a paper in 2012, where they have this projection estimator idea. Then you have linking a probability sample with the big data. This is getting a lot of attention these days. One paper heavily cited is a paper of River. It appeared in JSM Proceedings. Usually JSM Proceedings papers are not that cited, but this one is heavily cited because it's one of the few papers where he talked about how to reduce the errors from the non-probability sampling with the help of the probability sampling. Very interesting paper. And Kim has a different approach. More recently, it appeared in ISI review. Okay. Then, and big data, could be a non-probability sample. So I kind of introduce the problem quite in a generic way. Then, of course, we have this whole problem where we are interested in adding the undercount and overcount in the census coverage measurement project, for example. We link data, census data, with the post-enumeration survey, so that is there. And then in Germany and some other countries, they talk about registered assisted census. They have good registry, but they use a probability sample to correct for some of the biases. Then it could be useful in non-response follow-up. Well, if you can link multiple databases, you may have good auxiliary variables that you can use for non-response modeling, and that could be potentially useful. I have not done any work on that, but I know there is a paper at the Census Bureau. This is the interesting idea, statistical register. In statistics Norway, and I believe other Scandinavian countries, they have good register. And then what they do, they take the register, number of different surveys, administrative records, and they put it together in one huge file, one file with lots of variables. And I guess there is no immediate purpose, but it could be useful for multi-purpose thing. And a lot of statistical ideas involved, such as, imputation, for example, treating outlier and so on. Then I did some work here at the BLS long back, use of historical databases to reduce the extent of revision. So here I don't have to tell you this problem. For employment statistics, you have a first estimate and then you have a number of revisions. Okay, and this is an interesting problem because you have a very large databases, universe databases, which is not available at the time of estimation, but it will be there down the road, which you can use for modeling and hopefully getting a better estimate. And also, this is very useful for evaluation purpose. My former student, Julie, I don't think she's here. She works a lot on this database. I don't know what she's doing now, but I think still using this kind of thing. Linking several historical databases. If I have time, then I can talk about this. This is something very interesting. This is really a big data problem related to transportation. So they are interested in predicting short-term prediction of traffic using a large vehicle probe databases. Hopefully I'll talk about this. Then we can link record by record, say record or entity. So maybe person by person, business, establishment by business estimate at the unit level. You want to do it for a variety of purpose, or maybe just produce that data. Maybe you want to do some multivariate analysis where you don't have all the variables in one nice database. Maybe you have to get those from other databases. And here the problem is many times, and then most of the time I would say, you don't have unique error-free identifier that you can use to link record by record. So what is done, you use a number of matching variables, that's the term, like last name, first name, age, address, so on, to link it. So the first task is to link, and the second task is to how do I analyze it after you link. That will take care of the possible mismatch error. Because even if many matching fields match from the two files, it may not be the same entity. Okay. So I did some work with Mike Larson that appears in JASA, and now I'm getting back to this problem. I had a student, Ying Han, very good student. She wrote a dissertation on that, and she did many different problems. And this paper by Han and Lahiri appeared in ISI Review. Okay, but her whole dissertation is about record linkage. Then we have a statistical linking for addressing small area estimation problem. Here there is a purpose. The purpose is to improve the efficiency of the estimator, reduce the variability, right? And I just talked about it. And there is a huge literature on this. The book by Rao and Molina has hundreds of methods and models. So if you're interested in topic, you can read that. And I more recently has an application in Chile in poverty mapping. And the last one that I would like to say is data integration for the purpose of nowcasting, and that I would like to talk about a little bit, and that I presented in ISI meeting in Kuala Lumpur last month. Okay, so this is a list of problems. I'm sure that other problems you can list, but that may be enough. And let's go to some of these specific problem, and it also depends on the time that I have. So let's go to the last one first. So it's a data integration for the purpose of nowcasting. Well, what happened, I have been talking to United Nations for doing something related to SDG indices. We call it SDG indices, Sustainable Development Indicator indices. We have some more than 200 indices related to health, education, poverty, transportation, lots of, there are 17 goals, and more than 200 indices. And they are interested in lots of different things. One is, of course, they wanted to do at the disaggregate level, and that's why I went to Japan in the summer a couple of times to train people from more than 20 countries. But there could be other kinds of problems. For example, they want, it's not necessarily a small area. They may want some estimates, and you don't have data. And so I've been talking to my old friend in India. He is with the Indian government, a statistician, now in the Commerce Department. And he has worked on several surveys in India, and he said that poverty is one of the important things they consider. And they produce their estimate, poverty estimate, every 5 years. Why? Because that's when they talk about poverty line. And in India, there are territories, and they do it for those, and for urban, rural. And for each one of them, in here, because they do the poverty rate, like a head count ratio, based on what they call average monthly consumer expenditure. If your average monthly consumer expenditure for you, so based on that they have a threshold, and if your expenditure is below that threshold, then you are in poverty. So it's not income. And this poverty line determination is a very complex, cumbersome procedure, and I didn't understand the whole thing. But what I understood that in order to determine the poverty line for various groups, they have an expert panel, and they look at different kinds of data, okay? And they look at expenditure on food item, in different categories, non-food item, okay? And then they have this expert opinion, which introduces subjective error, subjective opinion. And basically, they determine the minimum that you get to maintain a minimum standard of living. Okay, and for food item, they determine the calorie intake from different food items, and they convert it to monetary terms, and then finally get the number. So it's a very, very complex year. And one thing they need detailed expenditure on a long schedule. For example, you have the maybe milk products. So that's a broad category, but you can further down like fresh whole milk, butter, cheese, and so on. And apparently, the expert needs detailed information to determine the line, and that is available every 5 years because it's a very expensive survey. But is they have data for average monthly expenditure from a short schedule. Because to get the average, you probably don't need the detailed schedule. Maybe you just need average of milk item or something, and you can get it. And usually they got it from the Consumer Expenditure Survey done by National Sample Survey Organization. But it's kind of interesting. Sometimes they may also not have that survey done every year, because they have what they call round, which is like 6 months or 1 year. And in that round, they may conduct 2 or 3 surveys, depending on the money they have, And usually expenditure is a big item there, so it's done. But maybe the Prime Minister say, I need this year, maybe they skip that survey. But expenditure would then be available from other, okay? So in any case, what you have is average monthly expenditure from every year, but not the poverty line. And one thing we did is how to get the poverty rate estimate from the knowledge of average monthly expenditure, and we chose the poverty rate instead of poverty line because poverty rate is one of the important indicator in the SDG index, in the SDG list of indices, not the poverty line, and they don't care about poverty line. Once they have the headcount ratio, they are generally happy. So here we found the modeling is very useful. We started out with a very simple model, not very complicated. So basically, the idea is very simple actually. So what we did, we used 2 years of data, 2009, 2010 to fit the model, and then we take 2011, 12 to judge how it is doing, okay? Because these 2 years, they have poverty. Usually they have it for 5 years, but something happened, they wanted to know poverty rate, so they had it into a 2 years interval. And so we tried different kinds of models because we have this aggregate data. There is no individual level, so that's another story. In order to get those is very difficult. But from the public database, we can get the estimates of the poverty rate as well as average monthly expenditure. We can get it. And we can get it for the states that we consider and also by rural and urban. Okay. So you can think about different kinds of model in order to build some relationship between the poverty rate and average monthly expenditure, right? You can just do a straight line relationship, which you did, but we didn't report. That's not very good. You can do logistic. You can take logic transformation and the fit model that I report, okay? Or you can do more sophisticated stuff, like what we did is a beta regression, and we did in a Bayesian modeling. So we thought we had just 17 points there, because we are doing, we have 17 states, we are doing separately by urban and rural. Of course, you can combine all the data set and do it, but we didn't do it. And so we went for beta regression in a Bayesian way. Package is available, and my student Das did it using RSTEM. And you can also do using classical method by maximum likelihood, but that's not very important here. So basically what we wanted to show that something can be done with this preliminary modeling. We have some result, and hopefully somebody would look at it and say, okay, maybe we can try something else, and maybe they can keep improving. So the main idea of this project is to bring some awareness of this problem, that it is not totally impossible to get some good proxy for poverty headcount rate. You can do something, and maybe they don't want to use it, but maybe some expert panel can use this as a new statistics that they can use in the decision process. Okay, so here are a couple of tables, and this is for rural. I don't think I have time for urban, so I didn't include it in this thing. So this is from the beta regression here, and this is what you get. The intercept is 1.15, and the slope is negative 0.001. So the auxiliary variable is average monthly expenditure. So you would expect a negative relationship between this and poverty rate, and so negative is kind of what one might expect. And then it's a Bayesian table, right? 2.5%, 97.5%. So if you want to think about 95% credible interval, that would be for slope, which is more interesting, would be negative 0.003 to negative 0.0004, very small, but showing there is something there in this auxiliary variable. Okay, so this is for rural areas. And then one thing I would like to say, why beta regression? Well, we are dealing with proportion, which is between 0 to 1, right? So if you do straight regression model, your estimate may go out of the range. And so beta regression will not do that. Basically, you model the mean of the beta regression, and in the process, variance also get modeled. So I have some details in the paper, but I think that's not that important. And then for the nowcasting error means we have this data from 2011-12, the poverty rate, and you fit your model using 2009-2010 data, and so you have the MPCE, which is the per capita expenditure. So you can nowcast. I'm calling it nowcast as opposed to forecast. Forecast is something in the future. This we are talking now, and this is used by many people in Europe, I understand, and so I just borrowed that term there. Okay, but the idea is similar, but the conceptual is different. And so nowcasting error means so you have the actual poverty rate that they computed by the expert panel advice, and then you have this model, and you can call it nowcast, and then you can look at the difference, and then you see I just compared logit and Bayesian beta regression. Nothing was available, so I always find it useful to compare with something. So we took logit with Bayesian beta regression, and you see that it is not doing bad, and modeling is like mean error is like 0.2, third quartile for the Bayesian 0.5, 0.52, and so on. So here, as I said, that there is scope of improvement here. This is not the end of it, but let me just show you the histogram that we have. So on the left you see the logit, and on the right you see the beta regression, and on the top here, I don't know whether this will work here. At the top here you have a zero line. So you see that the beta regression is doing slightly better than the logit, in terms of this distribution of the nowcasting error. But this is just the beginning, and you can think of many different kinds of error model. For example, here we just take the average monthly expenditure of all the items. Maybe it's important to break it up into food item and non-food item. Okay, or maybe you may be able to get some auxiliary data at the state level. And so, but as I said, this is more for trying this out, try to see how modeling can be pursued in this kind of problem, but there is apparently no solution. Okay, now I would like to go to the real-time traffic forecasting using big data. This I have done with my colleague in Department of Civil and Environmental Engineering at UMD, and we have been collaborating for some time, and with a math student, Ying Han, the name I mentioned earlier, who did work in probabilistic record linkage, but she also contributed here. Now she works for Gallup, from Gallup organization. Very smart lady. So she, and also a student in engineering. They're very good in computing. So here the problem is this. So let me just go over the slide. So right now, currently, what they do, if something happened, maybe some accident happened or something, they kind of advise the traveler to go to the alternative route. But the here idea is that if you can go continuous prediction, and if the traveler can see what's going on in real time, maybe they can make their decision there. Okay, so there is a paper appeared in that international journal of IOSS. So I can send you the journal so you can read the details here. So here the problem is we want to predict the travel time or equivalent to the traffic speed, what will happen, say, 30 minutes from now. So that's the problem. And here the data is coming from the cars, GPS data. So when you drive your car, and if you have a GPS device, maybe your cell phone or some other GPS device, your information goes to satellite, and they come back and they store in a center, they archive in a center in the University of Maryland, and we have access to this data. Okay, so actually this data called is VPP data, vehicle probe data, and they have data for many states on the I-95 corridor, and Maryland is one of them. And we looked at the Maryland data for this project, And what they do, they look at the travel speed for different segments of different states, and this segment is basically from one point to another for a road, some meaningful way, maybe two intersections, And the roads can be, like local roads all the way to the highway, So they have different speed. And in Maryland, they have a total of 12,000 something road segments. And the data is coming every minute. The data is limited. It gives you longitude, latitude, and it gives the speed. But huge volume of data. It comes every minute on every segment. Truly a big data problem. So I was interested in doing something on big data, and then I've been talking to my friend Cynthia on this thing. And apparently, in big data problem, you may have a specific problem in mind and see what this big data can do to you, or you may have just the big data and kind of invent your own problem, And so we went for this, we thought maybe short-time travel prediction would be important, especially in this mass scale using this data. And so you use this for this problem. So what you see here is for 4 weekdays in November, okay, on a specific segment, and this is the speed, and from the speed we can probably say this is a highway, some kind of highway, and this is the segment, So they have a lot of different segments, and different color represent different Wednesday of the week in November, and we are interested in November because there is something, Thanksgiving week, which may be different, and so we wanted to see what happens. And so the idea is to understand on what factor or factors speed depends. Okay, so because once we can when we can understand the factors, then we can think about models, for prediction. That's the idea. And I think in typical data analysis, that's what we do. We do a lot of plots, a lot of descriptive statistics, try to understand what's going on. And so this is one of these. And we have lot of such graphs here. So in our context, we borrow ideas from the small area estimation to solve a big data problem. And the idea is this. Here the problem is not so much on how accurate or how best you can fit your model, but you have to do this thing instantaneously. We cannot wait. Okay? And there are some machine learning techniques that my colleagues in computer science use using a principal component. We didn't go that way. And I was doing small area. I thought, okay, maybe we can borrow some idea from small area. So the basic idea is very simple. If we can detect some repeatability in the traffic pattern, then we can do something using the idea of synthetic assumption. So if you believe that models don't change drastically, maybe from 1 week to another, or maybe 1 month to another, we can fit that model, however complex that model is. Modeling is a very difficult exercise. You have to think about different kinds of different possible models, and then you have to select some of them, and then you fit the model, and then you do some kind of diagnostic. If you don't like it, and if it reveals some pattern, you go back to the first step and come. So it's like an iterative process, and it takes a long time, and you have to do it for every minute, And so the idea is very simple. So if we believe the idea of repeatability, then you can fit the model maybe well in advance, maybe in 1 week time, and then you have enough time to fit all the models, and then you go to the current week, and you just use the incoming data, fit into the model, you get the answer. Very simple idea. And I got that idea from small area estimation, and I like to call it small area forecasting. Okay, so So using the concept of synthetic small area estimation, we now propose a radically different idea of completing all complex model building and estimation well ahead of time. That's the key thing. Say a week in advance, and then apply the chosen model. So here the thing is, we are not restrictive on model. So you can use whatever model you want, and whatever data set you want to integrate. That's fine. But the main idea is that you would have enough time to fit this model so that you don't have to think about the model building operation at the time when you're getting the data. That's the main idea. Okay. So here, I'm calling it data integration because we are using historical data to understand the traffic pattern. And so, I didn't think a lot about this paper, because I thought it's just a small area idea. And then the engineering student, presented it in one of these engineering international meeting in Canada. And this paper got the first prize. I was so surprised. And then this paper also got accepted in a couple of weeks in IOSS. So I think the reason some people may like this thing is the idea of applying the statistical modeling to this kind of real problem, because earlier people are using machine learning tools. Okay, so let's, maybe I'll talk a little bit about that. So here is so what we did, data for 3 weeks in September 2016 are used to demonstrate the proposed framework, and 1 week data is used for the study. So for example, fitting week may be September 12, 2016. Prediction of testing week is September 19, 2016, and we did it a couple of weeks. Data from 2,654 segments, about 200 lane miles. Lane mile is like the length of the road multiplied number of lanes they have, which form the mobility corridor of Maryland are used. Over 15 days examined for all segments, the total size of the data is slightly over 57 million records. Prediction up to 30 minutes in the future for each segment for all the 15 days result in about 1.7 billion records. Truly a big data problem. And this is the network we studied. This is Maryland, that we studied. And we studied, the good thing about this kind of data, you can evaluate your method because you know the truth, right? And one thing I would like to point out that other than the repeatability, you know what's happening for the entire day a week before. But if we do our modeling only for the current time, you don't know what's going to happen there. So you won't be able to use this thing. So we got some, we computed RRMSPE. So basically it measures how far is the prediction from the actual value. And we got some encouraging results, and it's comparable to what other people are doing, what my colleague in computer science did. But you can always improve. For example, we did not use data from accident record or weather data. So those are a possibility, and the model is not restricted to that. Okay. It takes about 3 hours to fit and predict for the demonstrated data set using 8-core Intel Skylake processor running Python 3.5 on this I got from the student. I don't know what that means. Okay, so I could stop here, or it's 2 o'clock, but if you are interested, I can go further. Thank you.
Questions?
That last model, did you model each segment separately? Did you model them collectively?
Separately. We can do that because we are doing, we can do it for every segment, every day of the week, Yeah, as I said, the model is actually not restricted. One can think of better model, bringing in more auxiliary variable. Like accident data could be very useful, and they do have this kind of data in Google. The weather data could be another one. But the important thing about this methodology is that you do everything well ahead of time. So you have an equation basically, and then when the data comes, you just fill in. That's the main idea. And here actually we looked at ARIMA kind of model, and then the order of each component of ARIMA is from 0, 1, 2. Like we consider no difference ARMA model, 1 difference ARMA model, and 2 difference ARMA models. So there are how many? 27 of them. And so what we did, we do some model selection. We use BIC, but it can be any criteria. And it turns out that ARIMA 111 did a good job, but of course, I would say that's still a crude model, which can be improved further. And the key thing is the auxiliary variable, I think.
Okay.
Now that's okay. Yeah, the forecasting is that something you want to do in the future, right? And nowcasting we are calling the methodology is similar, but nowcasting we are calling because the population already exists, and then we want to see how to. We can call it nowcast or predict if you like. Yeah. Yes. Yeah, that's a very good question. And as I said, this is just a preliminary model we tried. And part of the problem is that getting the data, even this simple data, aggregate data, it was not that easy. Although because they are in different places and you have to bring them and all these things. But yeah, so as you get more information, you can do it. For example, I think the model will be strengthened if we use some current auxiliary data at the state level. And a lot of times you have that kind of data from administrative sources or census records. That might help. And also, other thing I felt that we have to understand the way the poverty lines are determined, and I don't have a clear understanding. And I understand they look at lots of different kinds of data sets, and we have to understand what they're doing, And I didn't talk to any one of them, but I suspect they are looking at the detailed schedule. That's why they do it every 5 years. So we can make up some auxiliary variable instead of just one average monthly expenditure. We can break it up into food items, for example, and also. There is a recall period. Some of the items, they have like 7 days, some of them 30 days, some of them 365 days, like more expensive things. I think here also we have that, right? Right, exactly. Yeah, so, right, like if you're buying egg or meat, it's like 7 days, things like that, And so, and if you're looking at medical expenses, it could be like 365 days. So that could be also a factor. And we have not studied those things carefully. One reason is, well, we don't have the data. That's one big problem. And the other problem is that we have small number of points, like 17 points, if we just do separate analysis. Urban and rural. Of course, we can pull it together and maybe we can incorporate some auxiliary variables. But if you have more data, then you can try out many different things. I feel that, even if you have very good model and try to estimate poverty that way, maybe the government may not be agreeable to this kind of method, But I think it might help the expert in making their decisions because they look at different data basically, and then you provide another auxiliary variable. Maybe that way they can, to some extent, simplify the method.
I want to come back to a rhetorical question. Standard errors. Long standard errors are all. Model generate
Well, yeah, this measuring uncertainty in small area estimation is a big enterprise. There are so many methods available, both in the classical side and also in the Bayesian side, and I have done work in both methods. So the classical side, by classical I mean mixed model approach. They try to incorporate the external uncertainty of the estimator using Taylor series method, parametric bootstrap, Jackknife. There are several methods available. On the Bayesian side, I have also done it. This work. They do, as you see, posterior variance. And I think, if we can determine a prior for the posterior. When I say prior, I mean the priors on the hyperparameters like beta and the variance component. And many people think they are not that important, but they are. If they are properly chosen, I think Bayesian method would be very good. And so recently I have done a work where we try to kind of synthesize these two approaches. Like, is there a Bayesian method that would give you some classical criteria? For example, you choose a prior. Under what prior? I'm talking about the prior of the hyperparameter. Under what prior you can get a good classical probability?
That's well known. They contract in the same. The credibility intervals contract on the confidence.
Not in the context of small area.
Under weak conditions.
I have not seen a lot of work in small area. I can send you the paper. There are a lot of work. In fact, there is a book which is called Objective Bayesian, and the book by my former postdoc Gauri Data and Mukherjee. They wrote a whole book on probability matching prior. I think you are referring to that. But if you look at the model, they are not small area model. And when you try to do this kind of thing for a more complex like that, it's very, very complicated. I can send you the paper, which hopefully will appear in JASA. Thank you.
If I was living in the same place, are you living in the same place?
Yeah.
Okay,